Can you cut to me? Okay, good evening to everyone across South Africa, and welcome to this, the first of the Habitable Planet online live events. As you all probably know by now, my name is Carl Palmer. I work here at the Access, which is the Applied Centre for Climate and Earth System Science. And my role is the Education and Training Programme Manager. And basically, in that role, running these workshops is one of the major things that I do. And so it's a great honour for me to be able to talk to you live today, which is something that's really, really exciting and interesting, experimental and different. It's the second year trying to do it, so we should at least be learning a little bit about how to do it by now. But I'm really, really happy to be embracing this new technology and being able to teach on such a wide scale across the whole of South Africa. So I'm hoping that everybody is sat somewhere across the country. I can see we've got a group already here in Fort Hare. I can see a group at the University of Venda. And I'm hoping that the rest of you are all here on time. Just to give you an idea of what we're going to do, is we're going to try and hold an event which links all of you up across the country. There's about 300 people doing the course nationwide. Everybody has the link to the YouTube feed. And so the idea will be that we can all contribute and all come together around this course and around the physics of the course and hopefully have a bit of a discussion. We have all of your questions that you sent in after the first 2 weeks. And so what I've done is I've assembled a panel of scientists who are going to talk about your questions and hopefully, we think, answer them. And really just try and start off a bit of discussion which you guys can enter in on. So what we're going to do is firstly I'm going to ask the panelists to introduce themselves, a little bit more about that. But just after the introduction, the format today is that we will work through questions that you have sent in, so it's your questions, and we'll do it in the order of the course. So we're going to start with, in the beginning, move through the simple model, not too hot, and then add the oceans and atmosphere as we did it in the course. So we're building up the models just like we did in the order of the course. If at any point you have a question, then we want you to put it to us. We want you to guide the way these discussions go. And the way to do that is to tweet to Habitable Planet 19, to post on our Facebook group, or to send an email. And then at the end of each section of the course, we'll have a little bit of time to go to those questions and answer them if there are any. So without further ado, I'd like to introduce to you our panel of scientists. And one of the first questions that we got on the course was from one of the iPlaneteers called Rebecca, who asked, what is it that we do on a weekend? So I'm going to go around the various scientists that we have, and I'd like them to introduce themselves, a very quick bit about what science they do, but then also very importantly what they do at the weekend, and it will hopefully go to explain some of the pictures that I put up on Facebook earlier. So I'll start here in Cape Town, go around the room. So Tahlia, you're up first.
Right, hi, my name is Tahlia Henry. I'm currently studying physical oceanography. Working on my thesis at the moment, so that's what I should be working on the weekends. But alas, probably according to the picture on Facebook, I surf quite a lot, and I think it's a perfect getaway to. Oh, there we go. It's a perfect getaway to. Just getting out into the ocean. Obviously, you get to enjoy the thing that you study the most. You're not thinking about Ekman depths or tides or currents or anything. You're just sitting, checking out the waves. You can completely chill and relax. So that's pretty much what I do on weekends. So, yeah. Thank you.
Hi, my name is Tebo. So I'm doing a PhD at UCT. And I work on wind. The general title of the degree is atmospheric science, but mostly I just look at historical and future wind patterns. As you might very well know, South Africa is investing heavily in wind power production. So we need to know what's going to happen with wind resources over the country in the coming years. So what I do is part of that program. On the weekends, I sleep. But when I'm not asleep, I try to run so that I can be tired enough to go back to bed. Otherwise, I do some work. Nothing very interesting. Yeah?
Thank you to Rendani.
Good evening, everyone. My name is Rendani Brauzi. I like to refer myself as Carl's right-hand man. I've got a background in environmental sciences, specializing in ecology. But currently, I'm more interested into communication science, specifically climate science communication. So during the weekend, this past weekend, I was at a popular place in Guguletu called Zoli. I was eating meat there and mingling with some friends.
Thank you very much, Rendani. And you guys might have seen that we've just been joined by a group, including Hector. So Hector, we're introducing ourselves, discipline, and also one of the students asked what we do at the weekend. Wow. So if you could tell the students what you do at the weekend as well, please.
Okay, thanks, Carl. My name is Hector Chikoore. I have done this and that, but my background training is meteorology. Of course, my first degree had some mathematics, then I did some meteorology in Australia, and then I've done climatology, and I've also studied meteorological droughts at the PhD level. So now I am an academic at the University of Venda, and I've just come here near Cape Town here with some of our students. Of course, previously I used to be a weather forecaster before I joined the universities. What do I do over the weekend?
It has to be PG.
That's a tough one. That's a tough one. Yeah. I do some sport during the weekend.
Thank you very much, Hector. I'm going to go from left to right as it appears on the main screen. So, Boitumelo, you're up.
Hello, everyone. My name is Boitumelo, and I'm in Pretoria. So, I'm an engineer in training at Eskom, and I'm studying my master's in computer engineering at Tux. And what do I do on weekends? I try to keep up with my training schedule, which I never do. I go to my club address and I try to keep up. But yeah.
Okay, thanks, Boitumelo. Next, I think that's Fabian. Fabian, can you hear us?
Hello, can you hear me?
Yes.
Yeah, I'm Dr. Fabian Defon from Zulu. I'm a ruminant nutritionist, and I've been trying to make sure that we have a lot of meat on our tables, as well as training some scientists. What do I do on my weekend? That's quite a lot. My weekend is so charged that no one will ever believe it. I'm a family man. I have a wife and 3 kids so far, expecting again. And so it's going to be a big family. So this weekend was my baby's birthday, 4th birthday, my last girl's birthday, or last but one. I took her out in advantage, was accompanied by my wife as well. I did send some picture to Carl as well. You could see I am, as an agriculturalist, I was busy on the farm doing my garden. I make sure I practice what I teach. And I eat quite a bit of organic stuff. On Saturday is my program. Very first thing in the morning, I play soccer. I play soccer with a group of guys, and then midday I do a bit of banking. And on Sundays, I go to church. After church, I make sure I spend time with my kids before I lose my parental advantages. That's it.
All right, thank you, Fabian. I'd like to move on to Hayley. And Hayley actually has a specific question from one of the Planeteers, from Manare, who wants Hayley to also answer who her supervisor at UCT was, please. So can you add that on as well, Hayley?
Okay. Hi everyone, I'm Hayley. I'm a marine earth observation scientist. I currently work at the Plymouth Marine Laboratory in the UK. The reason I'm here even on this live chat, even though I'm not in South Africa, is because I did my PhD in Cape Town. I finished it last year. During that time, my supervisors were Dr. Stuart Bernard, who's probably only about 10 meters or so away from Carl at the moment. He's at the CSIR. Professor Frank Shillington at UCT, and Professor Mike Lucas also at UCT, and another lady from the UK. My background, I mostly work on using satellite data to look at our oceans, in particular things like coastal water quality. My PhD work was looking at harmful algal blooms and red tides. So I'm an oceanographer, but who's kind of moved more into space-based measurements and things. At the weekends, I like to do lots of things. I actually sent a picture to Carl of a card. I don't know if anybody saw it. Some of you probably recognize the language on it more than I do. It's actually a Dutch card, a Dutch version of the game Settlers of Catan, which is what I was playing this weekend with some of my friends, one of whom is Dutch, another of whom is Italian, another French, another Portuguese girl. So what I wanted to show is that scientists tend to have lots of friends from lots of different places. And I spend my weekends with these really awesome people. So I wasn't going to post a picture of the sun because it's usually raining here. So
how is it Dutch, Hayley?
Terrible. Although I did recognize Stad. Thank you, Kapstad, for that one. You know, I could tell what a town was and what a city was thanks to that. And Dorp.
Okay, thank you, Hayley. And I feel at this point it's really prudent to point out, after last time we had Hayley speak, that Hayley is not my sister. I had lots of Planeteers coming up to me asking how my sister was and how great it was that I got her in the program. Hayley's not my sister, okay?
I don't know why that is. Is it the Britishness or the glasses? I don't know.
Glasses, I guess, but it was such a strong conviction. There wasn't even a need to ask.
Yeah.
Okay, Nkosinathi, you're up. You're up, Nkosinathi.
Hi everyone. My name is Nkosinathi Xulu. I'm currently doing my master's at the University of Venda in environmental sciences, and I'm specializing in geography. My supervisor is there with you, Carl. It's Mr. Hector Chikoore, who's a climatologist. What I do on weekends, that's a tough one. Again, usually what I do, I make sure I watch football, Kaizer Chiefs especially. I'm not a fan of English football, but then yeah, that's what I do on weekends. I make sure I watch a game of football now and then. Yeah, I think that's it.
Okay, thank you, Nkosinathi. I think that's everybody been introduced, so we can press on with today. So, what we're going to do, as I said, is we're going to go through each part of the course. I'm going to invite somebody to give a quick recap of what happened in that part of the course, and then I'm going to dive into the questions that we already have from you on it. So we're going to start at the beginning, which is the talk in the beginning, appropriately, which you may remember right back at the start of the course. You tuned in, you didn't know what to expect, you had signed up for this online course. Most of you probably didn't think you'd actually even do it when you did sign up. And you've got this guy talking to you in the beginning. You might remember that was me. You might think that I look a lot older now. That's because the video was done a year ago. But anyway, I did it a year ago. You watched it 4 weeks ago. What was it on? So we looked at, in the beginning, two things, really. The first was to think about the fact that I started off by posing to you the interesting observation that we now know over 10,000 planets, thousands of planets across the universe. That's quite an incredible statistic. And yet, of all of those planets, only one of them is known to be habitable. Now that's really, really intriguing. As a scientist, that warrants further investigation. And so I said what we're going to do for the next 10 weeks of this online course is we're going to break that question down. We're going to try and investigate what are the reasons that the Earth is habitable. So that's really the premise of the course. And for the last 4 weeks, you guys have been going through our lectures and our reading material and looking at, we start off with very, very simple physical models. Now, I'm originally a chemist. I know that we've got lots of biologists in the room and on the course, and I would argue that physics, far from being the most difficult, is actually the most simple. Physics is a lot less complicated than chemistry and biology, and it's proven by the fact that we started off with very, very simple physical models. But before we come on to those really simple physical models, what I'd like to do is take you through my talk, which was in the beginning, where I took you back to think about, okay, we made this observation that there's just this one habitable planet that we know of, but why do we have something at all and not nothing? And if you remember, I took you back on that journey to think, you know, how did you get to the lecture theatre, and you know, you travelled on the roads or your computer, and you travelled here and there, and you were born, and you didn't die before the age of 5, and I went all that way back. But then we went even further back. We had to think about the start of the Earth. That was 4.5 billion years ago. But then we went even further back to think, well, why is there an Earth? Why is there something and not nothing? And that takes us back to the theory of the Big Bang. And what I really did was I just outlined that 14 billion years ago we had this event called the Big Bang. And I said, why? Why does science think that? Why is this the contemporarily held view? And I gave you through the evidence. And to summarize the evidence very quickly, the one first observation, and that's really important, is that we can use the redshift, the fact that objects that are moving away from us look more red when viewed from our relative perspective. That redshift tells us that everything in the universe is moving away from us. And so we know that the universe is expanding, and all of you guys will have learned Newton's laws at school, right? And so we know that unless a force acts on something, things continue to move in that same direction. So as soon as scientists found that everything was moving outwards, if we turn the clock back, we know that at some point it had to be in the same place. So it's moving outwards, it had to go back, and if you work it back at the rate that it's expanding, we can get to this date that's about 14 billion years ago. That sounds a reasonable theory, and the fact that the universe is expanding backs it up. But what really nailed it was this story I told you about the Nobel Prize in 1979. Because scientists then did models, they tried to reproduce the early universe in particle accelerators and with computer models, and they realized that if this Big Bang had happened, then the whole of the universe would be at a fixed temperature cooler than that Big Bang. And they can calculate from, because you know when you crush stuff together it gets hotter, as it expands, it cools. They can calculate what temperature it should be at now, and then try and detect the radiation, and this comes to Wien's law, which we'll talk at later, the radiation emitted by matter at that temperature. And it turns out that the universe is at exactly the perfect temperature to fit the theory. Okay, so the universe has cooled down from that very hot temperature when it was all together, and it's now spot on, the absolute perfect temperature. And so that point was the point at which scientists accepted this theory to be proven. And so that's the scientific view. And I made a very big thing that, you know, we're on a science course, so I'm going to present the scientific view. And so we had the Big Bang, and then I made the big thing that stars need to be formed. Because the Big Bang just made hydrogen and helium. And I'll come back to that in your questions in a minute. And we can prove that it made it in the labs, in calculations, all very well modeled. It makes hydrogen and helium. But it's stars that take those hydrogen and helium atoms, force them together, and make the heavy elements. Okay, and the heavy elements like carbon and oxygen and phosphorus and nitrogen are all the things that we are made of. And that's why people say that you are made of stars. So we have the Big Bang, we have stars, and the star debris from a star forms the Earth. And that was really my first talk. So I'm going to go into some of your questions from the talk. I won't read out a whole group to start with because they're all on the same theme. And so I have from Eunice, they said the singularity at the beginning, prior to the Big Bang, how did it originate? The next one is Kaya asks, as cliche as it sounds, assuming the Big Bang is true, what created the singularity? I'll stop at those two. So, really, really popular question. What happened before the Big Bang? Well, how did the singularity, singularity is all of everything condensed into one small speck. How did that happen? What happened before that? there's a very famous fiction author in the UK who in the 1980s, when reading about scientists and how they were modeling 1 second after the Big Bang, split seconds after the Big Bang, she said, famously in a newspaper article, she said, screw 1 second after the Big Bang, we want to know what happened before. 1 second before, that's much more interesting. And unfortunately, it turns out that it's a nonsense question, and I want to try and illustrate why, but it requires quite a lot of background understanding, which I can't go too far into, but it requires an understanding of Einstein. And principally, what Einstein did with his general relativity is realize that space and time are actually two facets of the same thing. So when we think about different dimensions in space, time is just another one, and space and time are part of the same thing. And that's a bit crazy for us to get our head around, but he was able to prove it. And secondly, he showed that gravity happens because large objects warp space-time. So the things roll towards the sun, or are attracted towards the sun, because you have to imagine that the sun is weighing down on the fabric of space-time, and everything therefore wants to head down towards the sun. So gravity operates because very massive things weigh on the fabric of space-time. Space and time is one thing, it's pulled down by gravity. Now the problem is, if you imagine all of the matter in the universe is getting, if we run the Big Bang backwards, it's getting smaller and smaller and smaller and coming in on itself, that gets incredibly massive. And what Einstein was able to show is that at a certain point, as we approach the singularity, because of the weight of all of this forcing down on space-time, it forces space-time into one thing, and time ceases to exist. So, the question of what happened before the singularity becomes a nonsense question because there was no time. And so how can you say something happened before or after if time doesn't exist? Einstein and later Stephen Hawking make the analogy that the question is similar to asking what happens if you go south of the South Pole? You can't do it. And if we use that South Pole analogy, we can imagine that at the South Pole there is the singularity and the universe can expand only northwards. It's in one direction. And the different lines of latitude, we can imagine different universes. And that's how scientists conceptualize it. That from the singularity, many different universes could form. One of them is ours. And so one possible theory is that universes form all the time from a singularity, and they have formed with different laws of physics, and we just happen to be in one of them. But that having been said, a really important factor to note is that there's no observable evidence from before the Big Bang, because there is no time, and so it goes beyond the realm of science. And so that really comes down to a lot of those questions about what happened before the Big Bang. A few people asked, how sure are we of it? And I want to add, I mean, the Nobel Prize was awarded for proving the Big Bang theory to be true, back in 1979. That's a long time ago. And I've made a really big point in my lectures that science isn't a list of facts, and it doesn't prove definitive answers. What we do is we continually match theories to observations, and you get what becomes a gradually better and better answer. And so you can take, for example, why is summer warmer than winter? One answer is that because the sun is closer to the Earth in summer. That's a decent answer. It is in the southern hemisphere. But then when we discover a new observation, the observation that it's summer here when it's winter in the northern hemisphere, we need a better theory. That doesn't mean that the first one is wrong. There's merit to it, but we can find a better theory. We have the Earth tilt. That's a better one. One that actually lots of people would say is right. But actually, we need even better theories than that, because then if it's just the tilt, we would ask, well, why are seasons different at the same line of latitude? Why does India have a monsoon and somewhere else not? We need a better theory. And so science moves to better and better theories, but closer and closer to some underlying truth. And if it was proven in 1979, the high likelihood is that we're reaching a point of getting very, very close to what the theory is. So it's very unlikely that the Big Bang will change. But one last big thing before I let the Big Bang go, and that's that I told you the Big Bang only produces hydrogen and helium. And we can predict with some certainty how much hydrogen and how much helium it should have produced. And when we go out into the deepest, darkest space, we find that that's exactly the ratio we have. So what we observe in the universe is exactly what we would expect from the theory. So I'm going to say that for now, it's a very, very good very strong theory, and one that's unlikely to change. But as scientists, we're always open to new data. I'm going to go on to Fabian now. We had Langlichle, who asked, can we please engage with Christians and get their view on the universe and Earth formation? And Fabian, you have a comment on that?
Hello? Can everyone get me?
Yes.
Yes. So in the concept of Christians and science coming together, that's a very difficult one. I will just give you what I think about it and what I've, according to my experience as a scientist. What I'll quickly say is, I would repeat what Albert Einstein said. He said, science without religion is lame. But at the same time, when you look at it, he says that religion without science is blind. That is quite interesting, because these two are very big things that they've never ever come to a compromise. As much as science has tried to explain everything, science can never really give you a conclusive answer. You even go back all the way from evolution. If you look at Darwin, okay, and you look at that from that point of view, you see that even in the book of evolution, you would find that at some places Darwin is talking about some superhuman being coming about. So if we look at that, then we come back again. One of the scientists great scientists in University of California, Joel, who contributed in developing the dark theory of how evolution comes. He is a believer of the Lord. He still believes that is that supreme being. So, as much as we as scientists, we try to explain things, religion has a big part to play. And so their conclusion was that scientists have a vision of how things operate and life, and also when you talk about Christianity, they have a vision in looking at it. So they're thinking that if we could bring some scientists and great religious guys to sit around and look at the theory and bring a common concept. So yes, I do agree that we can find a way, but that is a difficult task, as many religious people are so intense that they don't want to believe in science. But with modern theories and so on and so forth, we see that at one point in time, we have to converge. The religious people and the scientists must sit together and put ideas. So I strongly believe that we could come together, but in a very gradual and slow process, because it is very, very sensitive.
Okay. Thank you very much for that, Fabian. I think it's always really important, a point like this, to bring up a quote from Galileo, back from about 400 years ago, when he was on trial for heresy, for saying that the Earth went around the sun. In his trial, he came out with a quote which I think is really important for everybody who's religious and a scientist to think about. And Galileo said that the Bible tells us how to go to heaven, not how the heavens go. Science tells us how the heavens go. And I think that's a really useful point of reference to make, to look at the limitation not of religion only, but also of science. Okay, so religion tells you how you should live your life, what you should do. And I want to make it very clear, science tells you nothing about what you should do. Okay? If you're looking at science to tell you what you should do, you're looking in the wrong place. Science is mute on ethics. Science tells you about how the heavens go, how the Earth works, how something works, how something operates, how we can develop. It doesn't tell you anything about whether we should do that. So a great example is nuclear weapons. Science tells you how to make an atom bomb. It tells you nothing about whether you should make an atom bomb. And that's where we go to religion, philosophy, etc. Okay, I'm going to move on from that to questions around whether we think Earth is the only habitable planet. I got one from Lindelo and one from Tapelo. Lindelo asked, how can we be so sure that out of thousands of planets that are known, there's no life, not habitable, except for Earth? When Titan, Saturn's moons, has mountains and also lakes. And then secondly, Tapelo asked, planet Earth is the only planet known to be habitable. Considering the possible existence of aliens, is there any sign of possible life in our galaxy? But Hayley is going to start us off on those, please.
Okay, so my first response to this, the short answer to it is that we can't be sure that there's not life on other planets at the moment. And I'd like to sort of answer it as well by asking another question. So my question is, how can we be sure that there's no unicorns on Earth? So at the moment, we have no evidence for them, and that's kind of as far as we can go. The same with looking for life on other planets. We currently don't have any evidence that suggests that there is, so we haven't yet found it. However, the universe is a lot bigger than the Earth, so we probably have a few more places to look than we do for the unicorns. So what's currently been happening is, and it's actually quite interesting, this part of the story, I think, and you'll hear about a guy in a couple of lectures' time called James Lovelock, who's quite famous for proposing this Gaia hypothesis of Earth system science. So he's kind of one of these people that was really involved in the thinking that underlies the Habitable Planet Workshop program. And what he did was he was actually employed to start looking for life on other planets. And he was thinking about, okay, what would I look for as an indicator for life? And he looked back at the Earth and thought, well, I would look for the things that we see here, things like an atmosphere of a certain character with different components in it. I'd look for maybe for water. I'd look for certain heat signatures, you know, or certain temperature ranges. This Goldilocks zone being a certain distance from a star, like our Earth is. So this is kind of how we start looking for life on other planets. But at the moment, we've not really found anything. There's some ideas that there may be some water on Mars, which may show some small bacterial life, possibly. There's probably no large things on there because we haven't seen any yet. But that's the sort of processes scientists are using to look elsewhere in the universe. And of course, because the universe is so big, we've got a long way to look. So we're currently developing new telescopes and things like that. It will help us look at things like other planets' atmospheres to indicate whether they might be habitable and suitable for life.
Okay, thank you, Hayley. I think it's really important to stress that I never claimed that Earth was the only habitable planet. I've been very careful to always specify the only planet known to be habitable. So there's maybe a little bit of a linguistic difference there, but I've always been very careful to stick on that side of it. Rendani, any questions on that side of things?
Yeah, so far it's still very dry, so you can continue.
Okay, guys, we need your tweets. Tweet in #HPW19. Going to move on then from the Big Bang and in the beginning to get a summary of Not Too Hot. It's going to be fun to ball.
All right. So, part of explaining why the planet is habitable is looking into the qualities or identifiers that we can say, well, these are things that we mean when we say a planet is habitable. So one of those things that's very important is temperature. And we are very well aware that we cannot survive in all temperatures, or multicellular organisms cannot survive all temperatures. So thinking about this, then the question is, of all these known planets, why is it that the Earth is the only one that we know to have the right temperatures to support life? And like any other scientific question, what we do is build a physical model to try and prove. So the hypothesis being that it probably is the distance from the sun. So that's so-called Goldilocks zone. So to investigate this question, basically, so which is what you had in the talk, was that we built a physical model. So we eliminated all other variables and took 3 rocks of different colors, therefore different emissivity, and tried to find out whether Earth would have just the appropriate temperature to support life. And what was interesting in that talk is that we found out that Venus which happens to be much closer to the sun, actually would have a lower temperature than Earth. That alone says that our theory that it probably is the distance from the sun does not hold water. And we found out that if it was the distance from the sun, then Earth would probably be at minus 18 degrees on average, and which is not the case. So from this, then we came up with a new hypothesis that what is unique to Earth is the atmosphere. So that's basically the short summary of the talk.
All right, nice one. Thank you to Boho. That was very nice. We had quite a lot of questions centering around that talk. I want to start with, we had a couple on effective temperature. Nuswari was one who asked, I'm not clear on the effective temperature. Does effective relate to measured or real, as opposed to calculated or model bounds? And the answer is really yes. What effective means is the one that we calculate in our model. So in all of the questions on the course, we were comparing the effective temperature. That's the one calculated in the model that Boho has just introduced, where all we've taken is a ball of rock, the right distance from the sun, no atmosphere, no ocean, the right color, and we've calculated the temperature. That's the effective temperature. And as Boho just introduced, it's freezing cold. We compared that against the observed temperature. And so we found, as Boho just said, Venus is really hot, Earth is right, and Mars is cold. Those are the observed temperatures. The effective temperatures are all really cold. And so we learned something from Dumasani's model, and that's that something is missing, and as Boho had hinted, that's the atmosphere. Another question we had is, what's the difference between the effective temperature and temperature, and the presence of the atmospheres on Venus and Earth? So we then got on to questions about Venus. And so I'm going to hand over to Boho to talk a little bit about Venus. Can you introduce the questions as well? Do you have them?
Yes, I'll take the one on Venus. So the question is, what effect does the thickness of Venus have on its temperature, looking at the point that it is much closer to the sun as compared to the Earth? Now, Venus is blazing hot, and so as we said earlier, it cannot be the distance from the sun. So it's not its size per se, but the size of its atmosphere that is responsible for the higher temperatures. And unlike Earth, Venus has what you'd call a runaway greenhouse effect. What that means is that it doesn't have a negative feedback system. It does not regulate itself. So the temperatures just keep increasing. Whereas here on Earth, we don't have a runaway greenhouse effect, which means that because of the circulations between the oceans and the atmosphere, the Earth has the ability to regulate its temperatures. So that's basically the two differences.
I mean, what's fascinating there, Boho, is that Venus has this really thick atmosphere, right? And it could go either way. I mean, if you think about a really, really cloudy day, then you could think it could be cold. So the thick atmosphere could have just bounced away all of the radiation. But because of the composition of the atmosphere, which is mostly greenhouse gases, rather than other gases that might reflect it away, the net effect of the atmosphere is to keep it warmer. In our effective temperature, Venus was really, really cold. So because it's got a very light coloured surface, it reflects away most of the light. But then add that atmosphere in, and it's boiling hot. And then, as you hinted at, it got the atmosphere by what's called a runaway greenhouse effect. And that's a really interesting one by comparison to Earth. They think that Venus used to have oceans. And then as it got hotter, the water evaporates. Water is a greenhouse gas. So it makes the planet hotter, which causes more water to evaporate, which causes more greenhouse gas, which makes the planet hotter, which makes more water evaporate. And it's a positive reinforcing feedback. But a really interesting case study in what could happen to Earth. All right, thanks to Bob. Moving on, we had a question from BC, who asked, Why is Mars not habitable? And what would the Earth be like if it had a higher albedo? Boitumelo, you're going to give us something on that.
Hi, can you hear me?
Yes.
Awesome. Okay, cool. Why is Mars not habitable? So far, in the group or the conglomerate of scientists, we all know that Mars is the closest planet in our solar planet to have at least to be habitable, or to have some sort of hope for it to be habitable. We know that Mars has certain relation towards Earth. Mars has soil, and it's not too cold or not too hot. There is enough sunlight to use on or solar panels on Mars. We know that it has a approximate relative of 38% gravity in relation to Earth. But there are no enough resources, or Mars doesn't provide that opportunity for us to grow planets or food on it. That's why Mars is not habitable. We can look at other effects such as the distance between the Sun in relation to Mars and the Earth. Mars is not approximately the Earth and the Sun. Mars and Venus were approximately on the same distance about 5 billion years ago. But we then came to a point that we know now that Venus is too hot and Mars is too cold. So that's why we cannot have sustainable life on Mars, because there is there's no resources for us to grow or to make life on Mars. I think that's much of others.
But there's a lot of CO2, right? I mean, so plants should love it.
Carl, come again?
There's a lot of CO2, so plants should love it.
Yes, there is a lot of CO2. Mars has a promising atmospheric surface on it, but it doesn't literally dictate that it can actually hold or it can provide life on it. Simply because we cannot validate that there is too much water. But although we know that the soil on Mars we can extract water from it, but we are never too sure that it can actually sustain life.
Did you see the news story with the running water on Mars recently?
Yes, I did.
And
but that just doesn't justify that they can be life. Like as NASA says, if we can prove that we can find some sort of bacteria on Mars, then that can dictate our whole theory that yes, we can actually sustain life on Mars. But other than that, if we cannot find anything like bacteria living on Mars, able to survive the conditions that are present on Mars, we cannot for sure validate our theory that Mars can be habitable.
All right, thank you. That was very nice. And the second part of the question, what do you think Earth would be like with a higher albedo?
It's from Tabello. Are other planets contributing to the probability?
Second question. What would the life have been like, Earth have been like if it had a higher albedo?
What would Earth be like if it had a higher albedo? Carl, do you want to take this one?
Anybody want to have a go on that? I guess just the answer is colder, right? To a first approximation. But what we'll find out later in the course is that Earth has a whole bunch of self-reinforcing feedback systems. Now, it would appear that if you just tip it a little way in either direction, particularly now, then it will either get very, very hot rapidly or very, very cold quite rapidly. So I would imagine it's quite possible that if you just change the albedo of Earth very slightly, it wouldn't have ever been habitable at all. Anyone else? All right, Boitumelo, but you can press on then. So we also had some questions about Earth and the other planets. And I found these were some of the really, really quite fascinating questions. You know, normally when I get questions on the course, I look through and I think, well, you know, I could probably answer that, and I have no idea about these. So it's a really interesting discussion. We had a few. So we had Nan, Tor, De Okosi, Tabello, and Sivwe. all asking, what's the relationship between Earth and other planets? Do the gravity of other planets influence the rotation and the position of the planets next to them, the adjacent ones? And are the other planets contributing to the habitability of Earth, or just spectators? So really, all of those to sum up, Boitumelo, it's what's the role of the other planets in habitability and affecting each other?
Okay, cool. I think the interesting question here is, what is the relationship between Earth and other planets? But Newton tries to explains the relationship between two masses if we can model down to a very simpler concept. If you have two objects that are placed to each other, their masses attract each other due to Newton's gravitational universal Newton's Newton's law of universal gravitation. Sorry. What the relation between them is, if you have the sun. Okay, let's just look at the sun. Let's just look at the Earth, the Venus, and Mars. We know that about 5 billion years ago, they were approximately on the same distance. But now we know that if we model the distance between the Sun and these planets in relation to Venus and Mars in relation to Earth, and looking at the Sun as a reference, we know that distance plays a role. That's why Venus, which is in front of our Earth, is too hot, because we can say it's closer to the Sun. But that's just a hypothesis. But then we look at Mars, which is too cold. The distance again plays a relation towards in comparison to Earth. We can say the reason why Earth has a sustainable life to it, or we can live on it, is because it's at the right distance from the Sun. So if you were to question if you were to place a question of relation between this, distance will actually influence the relation between these masses. I mean these planets.
If Mars was the size of Jupiter, would we still be habitable? Would it make a big difference?
Well, size does play an effect, or does play a role. We know that Venus is about 95% size of the Earth, and it has certain qualities or certain properties that the Earth has. Venus has the same core material as the Earth has, but the difference is if you look at the size or the proportion of size, the bigger an object is in relation to a smaller object, if you were to heat them up, we know that a smaller object will heat up faster than a bigger object. And if you were to cool them down as well, and smaller object cools down relatively faster than a bigger object. That means that size does play a major role. So if Venus or if Mars was a bit bigger, maybe we would see some sort of a change or some sort of a different situation than we see at the moment.
All right, thank you, Boitumelo. That was really interesting. I'm just going to, being distracted, go to the phone. Rendani, do we have anything? We're at the end of the section.
Yeah, I think it's maybe Boitumelo will answer this. It's a repetition. It's a question from Mwako Mohale. She's asking, should Mars be habitable? How exactly are we going to benefit as residents of planet Earth?
So if it was habitable,
yeah,
how would we benefit?
Yeah.
So let's imagine it is habitable.
Yeah.
How will we take advantage?
Okay. It's inevitable that we are not running out of resources on Earth. If you look at the rate at which our society is growing, especially with new developments in technology or infrastructure, we require a lot of resources, which is trees and space as well. Does take effect in it. So if Mars were habitable, we can invest our coming generation, or we can transport our new born babies to Mars so that they can occupy the space on Mars. And create a new generation. Of course, we cannot transport the entire Earth to Mars or half of it, but what we can do is we can transport Siemens that we can grow on Mars and create a new population. The idea here is not for us to run to Mars, but is to preserve the existence of humanity or human beings. So if Mars were habitable, we won't transport human beings in a large amount of numbers. We'll most definitely just transport Siemens to Mars to grow them on Mars, not actual humans, because that would be very expensive.
There's a movie out right now about called The Martian. Apparently, it's extremely scientifically accurate, and it's called they call it a homage to science. Apparently, it's a really interesting movie to watch as a scientist. So I'd suggest.
Yeah, I haven't watched it. I'm only going to watch it this Friday.
So, okay, moving on to the next section. That's not too hot. So we set up a simple model. We thought, okay, Mars is too cold, Venus is too hot, Earth is maybe just right in the middle here. And we set the simple model up, we find out that actually a ball of rock the right distance from the Sun and Earth wouldn't be habitable, it would be far too cold. Something's missing. And in light and air, we find out what that something is, and it's called the atmosphere. And basically, all we do with the talk of light and air is look at how scientists understand light, and we learned about how light can be conceptualized as both a particle and a wave. But when we use the wave theory, we know that red light is very long wave, blue light is very short wave, the shorter wave is high energy, the long wave is low energy, and that forms just a small, small part of a bigger spectrum of radiation called the electromagnetic spectrum, and that there are certain rules for how light and air can interact. And there are certain rules for how different objects emit radiation. So there's the two. There are rules for how we emit and rules for how we absorb, how particles absorb. And I'm counting us as particles, which we all are, I hope. We're all waves as well, curiously, according to quantum theory. But anyway, we'll be particles for the time being. And so the one rule that we learned is Wien's law, and Wien's law basically says that we all emit radiation all the time, which is a bit crazy for us because we look around the room and Rendani over there is not glowing, right? But that's because our eyes can only see this narrow window in the electromagnetic radiation. If we could see beyond that window, then we would all be glowing, and every object would. But then, of course, we couldn't see anything because everything would be glowing, so it would be useless. But basically, Wien's law, all it says is, as an object gets hotter, the wavelength which it emits becomes shorter. It emits higher energy wavelengths, which makes perfect sense, right? It gets hotter, it emits higher energy. And then we also looked at what happens to absorption. And absorption rules are quite complicated. I'm not going to go into them today. But the absorption rules dictate that visible radiation from the sun is transparent. The atmosphere is transparent to it. It goes basically straight through. That means that the sun doesn't heat the atmosphere, which is a mistake lots of people make. Actually, the sun goes straight through. That's why you can see it. But the sun heats the Earth. The Earth is able to absorb that solar shortwave radiation. And then because of Wien's law, the sun is very hot. It emits this shortwave radiation that goes through the atmosphere. The Earth is much colder, so it emits a much longer wave, much lower energy radiation that the atmosphere does absorb. And this is the key to what's called the greenhouse effect. The greenhouse effect is a good thing. It's what keeps the planet a lot hotter than this -15 that Dumasani calculated. So let's be clear, we need to separate the greenhouse effect, which is how greenhouse gases keep the planet warm enough, from global warming, which we'll talk about later in the course, which is basically too much of a greenhouse effect. Okay, I'm going to invite the owner of the next question to come read it. You can read from my screen, but it's your own question. Put it there.
Okay. I asked, can you explain the concept I heard in high school, maybe false or true, that objects don't actually have color. Their color comes from the frequency that is absorbed from light. Can you give clarity on this, if there's any truth in the statement, and how does it work with digital screens, and how color reflected back to us is the way we see it, since the screen is in my observation, not absorbing any light.
Nice one. Put that to Hayley, please. Thank you.
Can you hear me?
Yep.
Okay. This is one of my favorite questions. Color is an amazing concept. It's quite a bizarre concept. It's quite difficult to get your head around when you think about it too much. But generally, the statement that Flora just made there is true. Things are usually the color that they appear to be to us because of the way they interact with light. The case I can think of that's a nice example is leaves. They're green because they absorb light in blue and red and they reflect light in the green. So most things are like that, but you raised a really interesting example of why the screen's not like that, why they have different colors. Well, screens actually emit light, and they emit light at different wavelengths. So when you see it, they're emitting different wavelengths, different colors. So that's how that works. Is that clear? Does that make sense?
Yeah, that does. Thank you.
I'll add to that, Hayley. The screens, however, only emit 3 different colors, right?
Yes.
But we see all of the colors. And in that, there is an optical illusion. So, as Hayley points out, when you look at a leaf, you're seeing it's green because it's emitting green light. But when you see green on the screen, it's not emitting green light. It's emitting blue and yellow, one of each. But the detectors in your eyes, you only have 3 detectors. And they're able to detect all of the different wavelengths of light through using just those 3. But green light absorbs on 2 of the different reflectors. And so if the screen projects blue and yellow at the same time, it stimulates those 2 and gives you the optical illusion of green. And so what's fascinating is a leaf will look green to me, you, or a cat. But your TV screen will look completely different to your cat because they have different receptors. So the TV screen is just a model that's tricking your head into believing it's those colours, but for a different species, it will look completely different.
Yeah, that's a very good point. So color is kind of a funny concept. You can measure color with an instrument, which is basically what I do. The satellite data that I work with effectively measures wavelengths of light. So that, in a way, is color, but it's not necessarily exactly the same as what you perceive in your head. That's a model that your brain has for what you see.
Perfect. Thanks, Hayley. That was really nice. So next one, pardon me, excuse me. On a similar note, Koketso asks, according to Wien's law, shorter wavelengths are hotter and blue wavelengths are shorter and longer ones are red and colder. So she's saying that hot is blue because it's the higher energy, and that cold is red, and yet we use tap colours the other way around. And so this one's really, it's interesting how we've got that association, but it's quite a simple one. It's a confusion between heat and energy. So blue light is higher energy, right? Whereas red light is lower energy. But the type of energy that we perceive as heat is IR, infrared, which is quite low energy radiation. We perceive anything that's higher energy as light, it becomes cold. So although it's got more energy, it has less heat. And so the red end of the spectrum is representative of heat because it's closer to infrared, and infrared is what feels hot to us. So the next one we're going to is from Boule, who says, okay, my question is that if the Earth's surface is heated by the incoming solar radiation and some is reflected and re-emitted by greenhouse gases, does that heat ever reach the sun again? Okay, also a really quick answer to that question. The answer is yes, for sure. So the sun is huge, right? It's a very, very big object compared to the Earth, which is very, very small. And the sun radiates heat back to the Earth. Some of it, of that heat, is then re-radiated back out by the Earth, back into space. And some of it will reach the sun. But think about the relative proportions. And I looked this up. It's a bit like if you heat yourself some peas for supper, and you take one of those hot peas and you place it in one corner of your living room, and then you go and stand in the other corner of your living room. I mean, technically, that pea will be heating you up because it's hot, right? But you're not going to feel it. And so the sun is in the same thing with the Earth, right? The Earth is a hot pea in the far corner of the room. Yes, some of that radiation is getting back, but is it significant? Probably not. And then lastly, in this question, we have Afikile, who asks, what happens when sunlight is absorbed by sea or water? And I'm going to hand that over to Hayley in England.
Sorry, Carl, I've lost you. Can you repeat that for me?
Sure. The question was, what happens when sunlight is absorbed by sea or water?
Ah, okay. So this is pretty much my entire PhD, which is really cool. So when sunlight hits the water, the visible light that comes in from the sun is at all different wavelengths in the visible, from like 400 to 750 nanometers. So in terms of the visible portion of the light, it's absorbed in different ways depending on the wavelength. So the reason the ocean looks blue is because it absorbs more of the red light and reflects more of the blue light. Okay? And this changes with depth. So the deeper that you go down in the ocean, the more you lose that red color. So if you go diving and you cut yourself and you look at the blood on your hand, you'll see that it doesn't look red at all because there's no red light that's come in to reflect off that. So that's one way that light interacts with the ocean. And this has effects for things that live in the ocean, like phytoplankton, which are tiny microscopic plants, and they use different parts of the spectrum to photosynthesize. So the depth distribution of the sunlight is quite interesting for them and affects how they grow. In other ways, the light also creates heating. So when the light is absorbed by the ocean, it heats up, and this can create convection currents. So like the ocean that is warmed will circulate differently to the ocean that is cold. And that affects how our climate works.
Okay, thank you, Hayley. Bear with me 1 second. That's the end of the questions from the light and air. And Danny, anything on the phones?
I've got. I think this one is going to Boitumelo. It's from Exponiso Mjaja. Is asking, is it possible that there could be another Earth-like planet in another galaxy?
Well, since we've got billions and billions of galaxies, and the Milky Way galaxy is the only one that we sort of know, but we haven't explored all the sides of it or the entire galaxy, the possibilities of another Earth-like planet out there existing are high, because we've got hundreds, thousands of galaxies. So that we cannot dispute as of now. We just have to say, yes, they can be, but we don't know for sure.
And lastly, there is Nyla _2. She's asking, if we remove carbon in the atmosphere, do you think the planet Earth will be habitable still?
If you remove carbon from the air, Carl, please, over to you.
Anyone else? Sorry? Carbon dioxide.
No, carbon.
The only carbon in the air is carbon dioxide.
It's carbon dioxide. It wouldn't be. Carbon dioxide is one of the most important greenhouse gases. And greenhouse gases, like we talked earlier about negative feedback systems, where greenhouse gases are important in keeping the temperatures on Earth such that it's habitable. So once you do not have that greenhouse effect, then the Earth would be too cold. Like on Mars, if you remember the talk about not too hot, not too cold, Mars has an atmosphere, I think, 1/100th of the Earth's atmosphere, and so it's very cold. So basically, the planet Earth wouldn't be habitable.
All right, thank you, Taboho. All right, we're going to press on. The next topic is the circulating atmosphere, and Hector's going to give us a little bit of a summary about how a circulating atmosphere makes Earth habitable.
Thanks, Carl. Some would question why we are discussing the atmosphere under physics. Actually, atmospheric sciences are very much physical sciences. We study the atmosphere mainly from the fact that the atmosphere is a gas, is a fluid which obeys the laws of physics, the dust laws of Charles Boyle and Avogadro, and then also the atmosphere obeys the other laws of physics, the laws of conservation of mass, conservation of energy through the first law of thermodynamics. The heat added to a system is used to raise the temperature of that system or the internal energy of that system. Some of it is used to do work. And then, of course, we also know that the atmosphere is in motion, and therefore it should obey the classical laws of Newton. Newton's law of motion. The acceleration of an object of mass m is directly proportional to the forces, or the sum of the forces that are acting on that object, but inversely proportional to its mass. And so you find that it's so amazing that the atmosphere obeys the laws of physics, and you find that atmospheric sciences have developed much later compared, because they depended on the advances in, for example, vector calculus and differential calculus, integration and so on, upon which they depend. And so you find that there are commonly three traditions. First of all, you want to ask yourself, what is this atmosphere? What is it made of? And then you want to look at the composition of the atmosphere. What are the gases which are more important as far as circulation, weather is concerned? And then which are the gases which are important as far as life is concerned? For example, you were talking about carbon dioxide just now. One of the functions of carbon dioxide is to participate in photosynthesis, for example. You know, it is needed during the process when crops or plants manufacture food, and so it is also important in that aspect, in addition to being a greenhouse gas. And so you look at that, the chemistry of the atmosphere is important, and then you look at motions in the atmosphere, what produces motion. Some of the factors are extraterrestrial, some of them are, for example, the key driver of motion in the atmosphere is the sun. And so the differential heating of the Earth's surface produces different pressures, and then there are forces then that drive wind or air to move from an area of high pressure to an area of low pressure. And so that's the starting point. Then you bring in other forces which we shall talk about. Once air begins to move, you now need to talk about other forces which come in. For example, a Coriolis force, which results from the spin of the Earth. There is also gravity, which also affects air, which is rising or descending. And then there is also a centrifugal force, because the Earth is spinning, or even when the floor is strongly curved, you also need to consider centrifugal forces. And over land areas, there is also, for example, the roughness of the surface, which causes a friction or induces a frictional drag on air, which is moving, causing, for example, convergence as well as the deflection or change in the direction of the wind. And so one key property of the wind is that the wind, of all meteorological parameters, it is a vector quantity. We are interested in the direction of the wind. We are also interested in the speed of the wind. And this property of the wind, because the wind is actually the be-all and end-all in atmospheric sciences. And so as far as motions is concerned, and so because the wind is a vector quantity, that is why a knowledge of vector calculus is important in atmospheric sciences. I could go on and on, but let's leave it here for now, and then we'll engage further.
Okay, brilliant. Thank you for that. That was a lovely summary, Hector. So some questions on the atmosphere. We have Nwabis asking, what are the most abundant gases in the atmosphere, Teboho?
Oxygen, nitrogen.
Sure, which makes sense, right? And then the rest is very small. It's like 80-20.
The rest is like, yeah.
And then Sikalela asks, what about if the atmosphere was all made of nitrogen? Let's get rid of the rest. Would the Earth be habitable then?
Still me?
Still you.
No.
No, why?
We need oxygen.
Yeah, absolutely. I mean, everyone needs oxygen to breathe, right?
Yeah.
So I imagine the
That's a
answer is
simple one.
no. Okay, we have a question from Pindile, who asks, why is the mesosphere the coldest part of the atmosphere when it's the closest to the sun? Shouldn't it be the other way around? Hector, that's to you.
Yeah, that one I think has been touched on earlier. But this
just
is
reiterate.
Yeah, this is just the fact that the Earth's atmosphere is heated from below. The effective heater is the Earth's surface. Terrestrial radiation is readily absorbed by the atmosphere compared to incoming solar radiation, which is too intense. There's very little absorption. Only about 17% of incoming solar radiation is absorbed by the atmosphere. Some of it is absorbed in the stratosphere by ozone, and then there is also some absorption by water vapor and oxygen in the troposphere. But you find that the radiation emitted by the Earth's surface, which we call terrestrial radiation or long-wave radiation, is almost readily absorbed, except that which is lost through the atmospheric windows. And so you find that the effective heater of the troposphere is the Earth's surface, but you find that in the stratosphere there is also some heating taking place in the upper levels due to the absorption of UV radiation by ozone, which is itself an exothermic process. And so you find that the terrestrial radiation is much more readily absorbed by the Earth's atmosphere relative to the incoming solar radiation.
Can I come in there? I mean, what's really interesting I find about this, right, is that, okay, fine, so that's the explanation that we're all given, right? That it gets colder as you go up in the troposphere because you're further away from the Earth, right? And it's the Earth that's heating. That all makes sense until you travel to Joburg in the winter and realize that you're no further from the Earth, you're on a plateau, and yet it's freezing because it's at altitude. But it can't be because it's far from the Earth, because you're right there. So why is that?
Well, there's a whole range of reasons or factors that affect temperature. There's seasons. There is also altitude or elevation.
But we said elevation affects it because you're further from the Earth. But in Johannesburg, you're elevated, but you're not further from the Earth. So it's a nice experiment to test that. And surely it falsifies our hypothesis, right? Because we should expect Joburg to be as warm as the sea level because it's right by the heating.
No, but the structure of the temperature stratification is that as you go up, there is a temperature decrease of environmental air. Environmental air decreases as you go up. So you find that the warmest places are those which are near sea levels. You know, like in river valleys, like the Limpopo where I come from, it tends to be very hot because you are in low-lying areas. Of course, the other factors of like latitude, as you move towards the tropics, you tend to experience more heating. And then, of course, the coastal areas can be quite hot, like here in South Africa, during certain periods when we have coastal lows, you can have very hot conditions also. Even though there are weather changes which bring day-to-day changes, like when a cold front arrives, you can get cold air and rain and so on.
And also, obviously, air cools as it expands, right? And so more of the area with gravity it's more densely compacted at sea level because gravity holds all the air down there. So in Joburg, then the air is less dense because we're at higher altitude, and that would also affect to make it colder. Okay, that's a really interesting one, and thank you for that, Pindile. Next question is from Sinongile, who says, are the global air circulations, the Hadley, the Feral, and the Polar, significant contributors to the existence of the mid-latitude fronts, or are there other atmospheric phenomena that play a greater role than the three air circulations? I'm going to send that all the way up to Nkosinathi and Venda, please.
Yes, can you repeat the question?
The question's really asking, can we attribute our weather, our mid-latitude fronts, Cape Town's rain, to the Hadley, Feral, and Polar cells, or is there more at play than that?
To an extent, I think you can, because the circulation on a large scale basis, they do influence the type of weather systems that you have in different regions or different zones within the globe. Like, for example, the Hadley cell it influences the type of weather that you have in that specific area. And then as you go down or as you go further to the mid-latitudes, they are influenced by the Feral cell. And also as you go down to the poles, they are affected by the polar cell. So to an extent, they do have a role in the type of weather systems that you have because it's based on the type of circulation that you have based on that cell that is located on that region. So, but to summarize everything, I will hand over to Mr. Chikoore, who will add, and I think.
I think that was a good answer. Hector, do you want to add anything?
I think it was good. I think it was good because, well, mid-latitude fronts are formed in the paraclinic zone where the warm tropical air conveyed is called polar air. And then the cold polar air pushes the warm air above and forming a cold front. But he has put it okay in those zones, in those boundaries where the ferrule cell meets with the Hadley cell, you tend to have formation of frontal zones.
All right. And Nkosinathi, why do those cells move seasonally? Can you quickly explain that for us, please? We've lost Nkosinathi. There you are.
Actually, the movement of these cells are they are majorly influenced by the movement of what we call the ITCZ, which is the intertropical convergence zone, where westerlies, or I mean easterlies, they tend to meet. So what happens is that this zone follows changes in temperature changes. So you find that when the distance from the sun is concentrated more on the northern hemisphere, you find that this ITCZ will locate itself where the heating is majorly based. So that is why you find that when we're having our summer, it's because there's more concentration on our side in the southern hemisphere. So the movement seasonally is based from the distance and the heating from the sun and the movement of the ITCZ. And the Hadley cell, the ferrule cell, and the polar cells, they follow the movement or the migration of the ITCZ.
Nice one, thank you, Nkosinathi. I think that was very clear. This brings us to the end of the atmosphere section. Anything on the phone lines, please, Rangami?
No, it's still dry, apart from the comments from some Planeteers who are enjoying the love session so far.
It's always nice to hear.
Yes.
Nice one. All right, I've deviated from the lectures to add an extra section on the Coriolis force because there were a lot of questions on it, and I'm going to hand over to Tahlia next to me, who's going to just give us a quick summary about what the Coriolis force is, please.
Alright, so to begin with, I'm going to say that the Earth rotates to the east, right? And the way we can actually, and that's an anti-clockwise rotation. So any object that's not attached to, or that's not attached to the Earth's surface, we would then observe as drifting to the west. And the best way to to explain that would be if you look at the stars, the sun, the moon, etc. It all rises in the east and sets in the west. So that's a very obvious look at rotation. But what about something that's very close to the Earth's surface? That's very minimal very minimal deflection. How would we be able to explain that? And that's where Gustavo Coriolis comes in. So he's used Coriolis force to explain that minimal movement that we can't really see and that's not very obvious, and it sort of explains it for us. So it's by saying that all our ordinary laws of motion, how that behaves and interacts within a rotating reference frame. So to bear in mind that Coriolis force, the nature of it changes depending on where in the world you are, particularly for winds, for example. So deflection of winds in the northern hemisphere will deflect to the right, and in the southern hemisphere deflects to the left. Also, Coriolis force is very small, as we said. However, it does become greater, or the effect becomes greater over a longer period of time and also over a longer distance. So, which also means that those motions are being constrained by Earth's surface. Which means, looking at the equation of Coriolis force, we won't go into detail about it, but just looking at the horizontal component, that becomes the most important thing, and that's what we tend to look at the most. So, in a practical sense, horizontal deflection becomes greater when we move towards the north, towards the north and south, towards the poles, and gets smaller as we move towards the equator. And that's due to the rate of change of, you can see my hand, there we go. Rate of change of the size of the circles of latitude. So around the poles, those latitude circles are very small, which means the horizontal decreases, but as we move down towards the equator, those rings of latitude become bigger and bigger. And that means that our horizontal then increases, and then increases for the poles. So that, in a nutshell, is Coriolis force.
Nice one, thank you, Tahlia. And we had a question from Andisiwe, which was they wanted to know more, and I hope that that's given a good bit of background on it and really nailed it down. It's one of the really important concepts, and so something that's worth spending a bit of time on. The next question comes to when we were talking about the Coriolis force. I showed you all in Critical Eye with the Science Guy section that video of the professor at the equator and how he's showing tourists how the water goes down the plug hole one way in one hemisphere and the other way in the other hemisphere, except as I explained to you, it's utter nonsense. And so one of the questions that's come in is, please explain how the Coriolis effect in Kenya is a hoax so that I can better understand it. That's from Siva. Hector, you want to take that?
Yeah, I have seen, actually, I have seen some people arguing that using water going down a drain, and I've said those are too small scales to talk about the Coriolis effect. The Coriolis force is not always present. It is present only at considerable scales. For small scales, even in the atmosphere, for small scale circulations, you find that there is no Coriolis effect. That's why you find that dust devils, if you have seen dust devils or if you have seen a tornado can rotate either clockwise or counterclockwise because it is not influenced by the Coriolis force. And so you cannot use movement of water down the drain to explain the Coriolis effect. That is, it's a misunderstanding of the physics. However, I think the idea of Kenya here is around, because there is the equator passes through some area of Kenya. I think that's the point that needs to be emphasized. And I think she has said it clearly that the Coriolis force depends on two factors. In the atmosphere depends on the latitude, and it also depends on the wind. And so we use 2 omega sine phi u. That's the formula for the Coriolis force. Of course, omega is the rotation of the Earth, which is a constant. And the latitude is a variable, and the wind speed. So the stronger the wind speed, the stronger the deflection. And then, of course, if you are closer to the pole, you also have a stronger deflection. As you go to the equator, at the equator itself, you find that there is no Coriolis force. And in fact, that's one of the reasons why we do not have tropical storms forming in the equatorial plane within 5 degrees of the equator. Tropical cyclones, typhoons and hurricanes cannot form along the equator because there is no Coriolis force, and you need a Coriolis force in order for a cyclone to form. So you find that along the equatorial axis itself, you do not get the Coriolis effect. And I think that's the point that would be important to say, of course, because the equatorial plane is parallel to the axis of rotation.
The professor, I find, is he's a fascinating study of the interaction of science and people, because all of these Western tourists, they learned about the Coriolis force at school, and their teachers told them that if you flush the toilet in the southern hemisphere, it goes down the other way, and they just believe it. And it would be so easy if the public were thought like scientists, if they could be trained to be more skeptical. It would be so easy for them to just go and pull the plug out at home. And you'll find if you do it 10 times, it'll go down different ways. They could have just done it. But loads of people believe it, and they're passionate about believing it. They won't. We went to Kenya with a habitable planet, and we took students to see the professor as a learning tool, and to see at least 5 of the class of 40, when they saw his demonstration, they're like, no, Carl, you're lying to us. This is real. I've seen it with my eyes. This guy has done it. It's got to be real. And so I think part of the question is, what is it that he's doing? And it's important. It's just a magic trick. This guy, magicians can pull a card out of your nose and steal your wallet from you. This guy's just realised he doesn't know about the Coriolis effect. All he knows is that if he makes the water go down one way one side, no way on the equator, and the other way the other side, tourists give him hundreds of rand. And so why wouldn't he do that? It's a magic trick that he gets paid a lot for. If tourists wanted to see a different magic trick, he'd do it. So, part of the answer is, as Hector said, it definitely is a hoax. And the other part of the answer is, it's just magic. He's just a magician. He's got good sleight of hand. That's all he's doing. Okay, also on this is a really interesting question asked by both Bongani and Shimwari, and they ask, what would happen if the Earth's rotation stopped? That's a really, really interesting one. Nkosinathi, you want to have a go? Maybe?
Yes.
Did you hear the question?
Yes.
Go for it then. You're on mute.
My thoughts on this. Because the Ferrari cell, the polar cell, and the Hartley cell, just the circulation is influenced by the movement or the rotation of the Earth. So if it was brought to a halt, in my opinion, I think it will be impossible to have these cells which are circulating around the globe. So it will affect the movement of wind, the type of weather systems. It will be really difficult, in my opinion, to have weather systems over some parts of the world, because the rotation does play a major role in the weather systems of the globe.
I'd like to mention the elephant in the room here, right? That if the Earth stopped, it's really important that we all fly off. So it wouldn't be anybody to appreciate the weather. Right? If you just stopped it, right? We're traveling at a good 1,000 kilometers an hour, where we are in Cape Town. We would all carry on traveling at 1,000 kilometers an hour, and everything that wasn't tied down would leave. Well, yeah, as I understand it, this is really fascinating, that the three cells only happen on a rotating world. If you model a world that doesn't rotate, you just get the one cell, which is actually the Hadley cell, right, the original proposed one, which would be rising at the equator and falling at the poles. And that's what a school child would, given that the equator is heated and the poles are cold, that's what you'd think. But I don't know why. I mean, I'm not a great mathematician or a climatologist, but it's really fascinating that it's the movement, the circulation of the Earth that actually makes the three cells happen. So it would really completely change the world's weather. Anybody else?
Another thing that I read, I googled this earlier because it was really interesting, and apparently if the Earth stopped suddenly, like if it stopped like right now, because the atmosphere would still continue moving because it's not attached, the atmosphere, the friction would scour everything from the surface of the Earth, would make the surface completely flat, apparently. Which sounds quite terrifying, so I really hope it doesn't happen.
I'll step into the controversial and point out that there is a part in the Old Testament where God apparently stops the Earth. So all this should have already happened if that's true. All right, moving on. Does the Coriolis force have an effect in warming or cooling of the oceans? And that's from Nawavisa. Hayley, you want to pick that up, seeing as you're up anyway?
Yeah, I can definitely pick that one up. So I kind of mentioned this a little bit in the lecture. If you look at the section where I talk about upwelling, and this is what happens on the west coast of South Africa, if you didn't have the Coriolis force, you wouldn't get that upwelling necessarily, because it's the rotation that causes the water to move offshore, combined with the wind. So in that case, what happens in these cases is that the water moves offshore and the deep water, which is cold, comes up. So in that way, the Coriolis force does affect the temperature, because it affects the distribution of water between the sort of warmer surface and the colder depths.
Okay. Tahlia, anything? I know you're not down for it, but you're also ocean scientist.
I have nothing to add to that, so I'm just going to
Hector?
say yeah.
Well, just to say that if the Coriolis force affects the winds, the large-scale anticyclones, they also drive the surface water. So surface ocean currents are driven by the wind. And so you find that over the western side of oceans, you have warm ocean currents, and over the eastern side, you tend to have cold ocean currents as a result of that those anticyclonic gyres, which are also largely influenced by the planetary vorticity, which is in fact the Coriolis force, Coriolis parameter.
Yeah, I could actually probably add a bit more to that. Again, and this is actually what my thesis is on, it's the role of winds on ocean and surface currents and ocean flow. You can then take that down to a lower level, and this is where Ekman and all of that comes in. How, and again, use your Coriolis force to have to work this out within your calculations for how deep that effect actually goes down, or how far down into water carbon does. So it can also be surface, but your winds do actually penetrate below the wind below the surface of the ocean. So yeah, also has a lower effective water column.
Okay, so another quick question before we move on from Coriolis comes from Beatrice, who asks, can the Coriolis effect ever change? And I suppose maybe the question is, will it?
I think what we've all said, well, that it does change depending on where it's not a constant. It changes depending on where you are in the world. Will it? Well, yeah, well, it does.
If you move.
If you move, yes. If you move, place, it's not going to do anything. But again, rotational speed will decrease. Also, let me say, yeah, rotational speed decreases with the increase in latitude. So at mid-latitudes, your rotational speed decreases or increases, and it, obviously, we explained that earlier about the poles. When you have the poles, it increases. At the poles, at the equator, it decreases. So yes, it does change.
And temporarily, the Earth is slowing down, so presumably the Coriolis effect is slowing down. But I would imagine it's not significant.
Yeah. And it's a small little concept in any case. It's not something so.
Okay, that's interesting. All right, Rendani on the phones.
There's an interesting story. Apparently, Pluto is trending. NASA has made 2 amazing discoveries, which suggest Pluto looks like Earth. But I've posted the link on our Facebook page.
Nice one. Yeah, I saw yesterday that NASA announced yesterday that they were going to have a big announcement today, which seems a bit bizarre to me. They announced that you're going to have an announcement, and they made news.
Yeah.
The whole news story is going, NASA have announced that they're going to make an announcement. Bizarre,
Yeah.
but really interesting.
Yeah, it's very interesting. I've posted the link on our Facebook page. So, yeah.
Nice one. Thank you, Rendani. Yeah. All right, we're going to move on to the role of the oceans. So we started with our bare rock, we've added atmosphere, and we talked about how the spinning Earth gives us the Coriolis spots. But now we're going to look at the role of the oceans. Nkosinathi, why do we need an ocean in a habitable planet? Is he there? Yes, there he is. He always seems to be building up to it. Nkosinathi?
Yes, Carl.
Why do we need an ocean, Nkosinathi?
Okay, thanks. Number one, we need to understand that the oceans, they account for the largest part of the planet, and they consist of a variety of marine species. And that we need to also to know that circulation of the ocean is majorly linked to the circulation in the atmosphere. So when we are talking about the atmosphere, you cannot not mention the role of the ocean. So they both have an influence on each other. But the difference between their circulation is that the atmosphere circulates rapidly, while the ocean circulates much more slowly as compared to the atmosphere. And this influences the type of weather and climate that we have over the globe or over regions. So what is an ocean? It is a very large expanse of seawater, in particular, where the main animals are given their names and they are divided geographically. So this is why we call an ocean. So a brief summary about the oceans. The oceans consist of a vertical profile. If you take the vertical profile of the oceans, you find that the temperature within, as you go up or as you increase in height, you find that the deeper layer is much more colder, and when you go to the top, you find that it's much more warm. Why is this? It's because the oceans are heated from above, unlike the atmosphere, which is heated from below. So the atmosphere is heated from below, while the oceans are heated from above. And you find that the oceans are a source of moisture. So when you mention or talk about the oceans, we need to understand that they are a source of moisture. Another important factor is the currents, the circulation of the currents, which are majorly influenced by the rotation of the Earth. That is why you find that the circulation, the current on the western side on Southern Africa circulates in a direction which is anti-clockwise, and you also go to the eastern side of Southern Africa, you find that the circulation of the ocean current is somewhat anti-clockwise. So the influence of the rotation of the Earth does have a major role in the flow, in the movement or the flow of the ocean currents. So these currents play a major role in the type of weather that you have over regions. For example, we find that the eastern side of Southern Africa is moist, and the western side of Southern Africa is dry. And ocean currents, they play a major role together with the winds. We cannot take away the winds when we talk about the movement of the oceans or the circulation of the oceans. And as I mentioned before, it consists of ocean currents. You find that there are warm currents and also cold currents. And then another important factor when you are talking about the oceans is the ocean conveyor belt. As I mentioned before, that the ocean is not a still body, it consists of circulation. So you find that there is this constant motion in the ocean in a form of this concept which is called the ocean conveyor belt. This system in which is when water moves between cold depths and warmer depths which are on the surface in the ocean. So you find that this motion is caused by a combination of two things, which is temperature and the salinity of the water or of the water that is in the ocean. You find that the deep ocean, there's a deep ocean, a deeper layer, and also an upper layer, which is driven by wind. So we call the upper layer or the surface layer as a wind-driven system or as a wind-driven concept. So you find that the colder parts of the oceans are what? They are salty. You find that the water is somewhat dense and then it sinks, and then as opposed to colder water, you find that warmer water is less dense, so it tends to remain on the surface.
Nice one.
I think. Oh, another brief concept about the ocean is ENSO. I think when you talk about ENSO, you are talking about the circulation over the equatorial Pacific. You find that the equatorial Pacific consists of winds, mainly which are called the trade winds, which flow from east to west. So you find that in some parts of, or in some occurrences, you find that these winds tend to weaken. So when they weaken, you find that the cooling of the sea surface temperatures tends to be elongated, and you find that a larger portion of the equatorial Pacific tends to be warmer. This is where we call, this concept is called an El Nino. But then you find that when these trade winds are somewhat stronger, and then they are pushing the sea surface temperatures towards the west, where the accumulation of warm sea surface temperatures is on the western side, that is called a La Nina. So this rotation over the equatorial Pacific influences the type of circulation that you have over on other oceans, which are on other parts of the globe. And simply because this is a telecommunication, you find that what happens in the equatorial Pacific communicates with the occurrence over the Indian Ocean by Southern Africa. That is why you tend to find that tropical cyclones tend to affect us on the eastern side of Southern Africa when you are having a La Nina on the equatorial Pacific. So you find that this telecommunication plays a major role in the type of weather, in the type of climatology and climate that we have in different parts of the globe. So I think in summary, I'll stop there. Thank you.
Thank you, Nkosinathi. That was a wonderful tour de force, and I think took us even further forward than we needed to be. I'll come to El Nino now, but I just want to pick up really quickly that one of the nice things I liked about Nkosinathi's talk was this distinguishing that the atmosphere and the ocean both make the planet habitable because they redistribute heat. Right? They take heat from the equator to the poles. But the big difference, there's two big differences between them. The first is that the atmosphere is heated from below, whereas the ocean is heated from above. So you expect the atmosphere to be unstable because hot stuff rises, whereas you expect the ocean to be stable. Now there are exceptions to both, but mostly the ocean is stable and most of the atmosphere is unstable. And then the second thing is the atmosphere has a very low specific heat capacity, so it takes a very little bit of heat, but it does it quickly. Whereas the ocean is very slow, but has a high specific heat capacity. So the ocean takes a lot of heat slowly. And then he came on to talk about this really fascinating dance between the two of them, which is El Nino. And that was going to be the next question. And Tembani asked, I'd like to know a bit more about the atmosphere and ocean and the relationship in El Nino, La Nina. I think we pretty much covered that. You want to add anything?
No, well, I mean, you mentioned now, and it's such a good question as well. I mean, like you said, nothing happens in isolation. So you've got this incredible relationship between atmosphere and ocean, particularly with your heat badges. which would be the sum of, and pretty much the sum of everything, the sum of all your heat fluxes both in and out of the ocean. And particularly with how your El Niño and La Niña is formed, you've got the whole switching of your pressure system. So what would normally have been your area of low pressure system is now suddenly high, and vice versa. You've got trade winds that are slowing down, they're speeding up in other regions, and of course that is just a temporary climate shift or climate change for the Pacific tropical side, or the tropical side of the Pacific Ocean at least. Yeah.
And while I've got you going, let me give you some more questions. Okay. So we're on to sort of oceanography now. Bantu asks, what causes sea waves? And then I think I'm going to give you the next one as well, which is Lunga, who asks, so what would happen to the movement of water if there was no wind?
Okay. What causes sea waves?
Kind
of. All right. So what happens, what causes sea waves? Predominantly wind. That's what we've been talking about, wind speed. Then there's something called a fitch, right, which is the distance of open water that wind is blown over. So that's very important. And then the width of that area, so the width affected by the fitch. Also time duration of wind blown over the area and water depth. Waves can also be caused directly, well, like I said, directly caused by the wind. And also swell that's generated from away from where that main area is. So you've got your big weather systems happening at open oceans and it's pushing into your bays, which are obviously now you've got waves moving from different mediums, from a deeper medium into a shallow medium, which will lead to your breaking waves or your swells turning into breaking waves, which is great for surfers. So, yeah.
Nice one. Thank you, Tahlia. I'm going to move on to Nuntuzelo's question, who asks, how do plants survive under the sea without sunlight? And do plants and animals under the sea get affected by the Coriolis effect? I'm going to put those to Hayley, if you're still there. Hayley, you're looking very dark. Oh, there you are. But we're just focusing on the Coriolis effect.
We're going into winter here, so it's getting quite dark. Yes, so in terms of plants, well, the thing about ocean plants, or as they're more commonly known, phytoplankton, which are little photosynthetic organisms that live in the surface, they can't actually exist without sunlight. You don't find them at depths. So the only photosynthesis that happens in the sea happens in the sunlit zone, to answer that question. So when you get places that are very dark, such as when it's at night or when you have very short day lengths, you get less photosynthesis. This is how the seasons of phytoplankton blooms happen. To answer the other question about organisms that respond to things like the Coriolis force and tides, well, some examples I can think of are, again, phytoplankton. They're in the in the west coast of South Africa. They're very dependent on the upwelling season, which is driven partly by Coriolis. So without those features, you wouldn't get the same growth that you get in the seasonal blooms. And in terms of tides and things, you have lots of organisms that depend on tidal cycles or have evolved to exploit tidal cycles. So things that live on rocky shore ecosystems, in rock pools and things like that. So they're all affected by tides.
Okay, nice one. Thank you, Hayley. I'm going to move on to Boule asks the question. I just want to know what causes heating imbalances throughout the Earth system, and I'm going to leave it at that. So, I think we've covered that. Several points. I mean, really, the main source of heating to the Earth system is the sun, and Nkosinathi talked about the intertropical convergence zone. So basically, because of the tilt of the Earth, most of the sun will hit the Earth around the equator between the tropics as the Earth tilts from summer to winter. So that means that larger amounts of radiation get to the equator, and with very little gets to the poles. And so that's really the big imbalance, and that's why really we have weather and we have ocean circulations in the first place. It's because of that heating imbalance. Next question is from Mondi, who asks, how does air circulation affect the temperature of the oceans, and how do models project ocean temperatures? So the lady next to me.
All right, so when I think of air circulation, you think of winds, how, so looking at, and I'm sure Dr. Hector, so you can also weigh in here. I think of ambient temperature, all right, so as simple as if ambient temperature drops, your SST, your sea surface temperature will drop, and also decreases your amount of absorbed solar energy, and then vice versa. If it's increased, ambient ambient air temperature has increased, your SST has increased because your solar energy has increased as well. So simply, if you think your polar regions, the air is pretty cold. You're going to have colder sea surface temperature. You think of your warm tropics. There's more absorption of light or solar energy at least, and you've got warmer temperatures or sea surface temperature. Also, you spoke earlier about the ocean circulation. And upwelling, so if you have, instead of upwelling, I would rather say overturn, which is something slightly different. If your winds are strong enough for a shallow mass of water, a shallow body of water, it can actually affect all the way through the water column, and you'll have the wind turning over water, so you've got cooler water at the bottom and warmed water at the top, and you now have a turnover of that water, which can be wind-driven, current-driven, but obviously because this is an air circulation question, they'll say wind. So which now brings cooler waters to the top, and your warm water then sinks down to the bottom or subsides.
And do you have anything on how the models predict ocean temperatures? So I throw that open.
Yeah, we can tell. I mean, to predict this, you'd use a model. I'd use an IBM model, which is an individual-based model. Again, you wouldn't actually just put one factor in there. You'd have to put lots in there. So particularly for oceans, because, like we said earlier, nothing occurs within isolation. So I'd put in factors about currents, wind, and now we want to look what affects the temperature. Currents, wind, anything changing in the atmosphere, your heat budget, what your heat fluxes are. You can put all of those into your modeling program. It does amazing maths and then can start pushing out data. Also, you want a long-term data set as well. Wouldn't go for just the snapshot data. The bigger your data set of temperature variation, of course, you can make bigger and better predictions, and your model can be more accurate.
Okay, thanks. Hayley, you want to add anything there on modelling of surface temperatures?
Yeah, I'm actually taking part in quite an interesting project at the moment, looking at parts of how we model ocean heat fluxes. This is part of the work that I'm doing using satellite data. And one of the things that we're looking at is how to include how the absorption of light varies over depth in the ocean into models. So at the moment, we make assumptions about how much of the light is absorbed at the surface and how much is absorbed at depth. But this actually varies depending on what's in water. In the case of like a phytoplankton bloom, you would have more light being absorbed at the surface than at depth. And obviously this can affect how the ocean is heated. So that's something I've been doing to help improve model parameterizations.
Okay, thank you, Hayley. So that brings us to the end of that section. Anything on the phone lines?
Yeah, we've got on Facebook, Divani Rensky Dramova says the Earth's energy budget is an important factor. What role does it play in the circulation of the oceans? I think this one goes to Hector. It was covered.
Yeah.
All right. Okay. And this is also another interesting one. I think this one goes to Hector. If the Earth stopped rotating, will we be stuck in one season? That's from Tandolwe to Astrid.
Okay. I think seasons is another thing altogether, you know. And so I don't think if the Earth stopped rotating, we would not have the traditional summer, autumn, winter, and spring.
Rotation is night and day, right?
Yeah.
So we'll be stuck in night or day.
Yeah, because revolution is
actually, would you have a year, 6 months of day and 6 months of night if it was not rotating? Is that right? As the Earth came around, then you would have 6 months of. So you would have 6 months of each day and night. Hey, interesting question. Yeah, the phone lines. Anything else?
This one comes from Simunye Nene, that's on our Facebook page. How will other factors, such as gravity, nitrogen content, affect the habitability of other planets such as Mars and Venda? I think this one is covered.
Yeah. I think we're covered. Yeah. Okay. Anything else?
I think so far. So good. We can proceed because I can check here on my time. It's 10 before 8, so some of us
we've got one topic left, so I think we're doing all right. And to take us into that last topic, I'm going to hand over to Boitumelo, who's going to tell us a little bit about why modeling is important in the story of a habitable planet.
Can you all hear me?
Yes.
Hello? Okay, cool. Sorry for that. Okay, cool. So yeah, this section is about the introduction to modeling. So we have went through some interesting topics. So we talked about in the beginning of the universe, or the creation of life. Then we went to not too hard. Then we did these sections. We talked in the beginning. We talked about singularity and how Albert Einstein explained the phenomena of singularity, and how our physics as we know fails behind or beyond singularity. Then he then explained time and space and as dimensions in this region. We talked about not too hot, the concept of Mars, Venus, and Earth in relation to the sun's distance, and all those. I'm trying to bring you back to the conclusion to understand why we have to end up with introduction to modeling. So we went to light and air. We briefly spoke about Wien's law, the greenhouse effect, and atmosphere, coriolis forces, and oceans. So what is introduction? What is introduction to modeling? The main or the key points that we have to ask ourselves is, what is a model? And how do we develop a model, and how do we use it? Why is modeling important? Those are the fundamental concepts that you have to answer as a scientist. Because let's put things into perspective. Scientists, what scientists do, we learn the universe. We try to understand things that are happening on Earth and outside the boundary of Earth. So when we try to conduct such experiments, it turns out that they might be a bit pricey, or the budget might be higher, and we cannot further our investigations. So we try to conduct experiments that are economical, repetitive, easy to construct, easy to analyze, and all those points sums up to what we refer to as modeling. So I'm just going to briefly describe what a model is. So a model can come in many shapes, sizes, and styles. It is important to emphasize that a model is not the real world, but merely a human construct to help us better understand the real world systems. So in general, models have an information input and an information process. So the information process is the behavior, and an output of expected results. So let's take, for instance, the Earth, Venus, Earth, and Mars. So you've got the sun at the specific distance away from the study planets, and it's exiting, or it's emitting heat into this some sort of an input to our system. Then the Earth and the Sun and Mars and Venus, they receive this input in different response. So the Venus traps the heat because of its atmospheric layer or surface, and Mars doesn't trap the heat. Earth just traps the sufficient amount of heat for us to have a habitable planet. So in just a summary, so if you were to point out exactly what a model is, what is modeling, you have to look at the very specific rule of thumbs. So first of all, never confuse a model with reality. And unvalidated model is an invalid model. So every model that we have, it has to be validated. And models are a means to an end, and not an end in themselves. So Carl, do you have the questions with you?
Yes. Are you sure to them?
Okay, yeah, I think I do have. Sorry.
But the first one is a really interesting general one, which you can kick us off on, which is as to what makes a good model.
Oh, cool. This is a very important question. What makes a good model? First of all, you have to understand what you need to model a phenomenon, because what science tells us, models are used in science to explain phenomena. So you have to define exactly what you're trying to model. So the first thing that you do is data mining. That's very important. And interpretation of this data comes later, after you have your data. And the third key point to this is parameterization. So parameterization is you look into what input goes into the system. For example, if you were to do climate modeling, the inputs that you look into is temperature, toxic gaseous substances, greenhouse effects, ocean and space, weather. That's what makes a good model. In summary, lots and loads of data that can be interpreted. The second question is from Langelitle. So he asks, or she says, how are models created and how reliable are they, since models are based upon calculations and assumptions? So this is just a rule of thumb. How are models created? First of all, like I said, never confuse a model with reality, and do not validate an unvalidated model. So you put your model into test and you validate its behavior. And one thing that you have to understand when you create a model is to understand that you already have an idea of what your model has to behave like. Let's take, for instance, the concept of a real world car. So if you were to model the movement of a car or how a car behaves on the road, you can't just build a real car because it's very expensive. So you build a small model of the car. You know that a car uses 4 wheels. The car has some sort of power into it, and that power gives the wheel motion to rotate. So with that simple concept or approach, you can further model your models. That's how you create models. But then you have to understand that we have different types of models. You have what you call a mental model and a conceptual model. So a mental model is more personal, it's internal, it's sort of idiosyncratic, and it's incomplete. So if you and I are looking at a tree or a color, for instance, I can perceive the color as in the color yellow. You can see the color green. That's just our mental model. So they're not validated. They don't have some sort of equation appended to them. It's just the way we interpret information by ourselves, within ourselves, and we reason with ourselves. But then a conceptual model is what most scientists use, or actually not most scientists, all scientists use. We try to understand the phenomena of the real world, or things that happens in the world. Like we just went through some interesting topics. The oceans, your light and air, all those sections. If we try to come up to an understanding of how we can create models that can represent or that can interpret what we just talked about, we have to understand the parameters that goes into what we just talked about, like light and air, oceans, and atmospheric temperatures. I guess that makes it, right?
Boitumelo?
That's okay, right? Yes?
Yes, we're out of time. It's 8 o'clock, so I want to start drawing things, line under things.
I think this is the last one. Should I stop here?
Sorry?
Should I stop here?
If you'd like to, or is there one thing that you want to say about modeling before we start to round off?
Okay, the last question from Ntwari. She asked, how far deviated does a model have to be until it is wrong, assuming all models are wrong? So this is a very easy concept. Question. We just take, for instance, the value pi. Pi can be approximated as 3.14, or it can be taken as the whole rational number with infinite float numbers into it. So how far a model should be deviated away until we say it's wrong? If you say pi is approximately 3.1415, we can sort of say, okay, that's okay. But if you say pi is 3, that's definitely deviating away from your approximations. Carl, I think I'm okay.
Perfect. That was a really nice, really good summary. Thank you so much, Boitumelo. I've just saved, before we all go and head home, I've got a few of the questions that were a bit more fun and have very quick answers to go through at the end. So I'm going to really just quickly run through those, and then I'll close up. So these are the quick ones. And Busso asks, why is Earth the only habitable planet? Right, that's the whole point of the course. So watch the course. That's the whole point. I mean, why would we have that as a question? That's the whole point. Watch all the course. Okay. Tandawetu says, can I have breakfast recipes? Hayley.
Follow me on Pinterest.
Perfect. Thank you. Bunty says, other than making Earth habitable, what's the importance of the greenhouse effect on people? I mean, it would be freezing. We'd be dead. Okay, so that's really, I mean, what do you mean other than the fact that we'd be dead? We'd be dead. Okay, so that's that one. Nkosinathi says, can anyone from any discipline take the course? Yes, you're here. Okay, you're already here. We're doing the course. Kwamba says, I have too little information for this. My question is, why is Earth the most habitable? Again, that's the topic of the course. We'll try and explain it. Sibusisu says, I'd like to find out about the Big Bang Theory versus God and the origin of the universe and the galaxy. We've done that. We're not talking about God as it's a science course. Fabian talked about it. Done. Now Visa said, if another person suggests that Dumasani's model is incorrect or not useful, what would be the possible solution? To show them how useful it is. We just talked about it. Caravo says, why do we do the readings if they're not in the test? Fabian, are you still there? You had an answer for this. Is he there? Yes. Yeah. Fabian? They're all looking like he's not there. Fabian! Don't leave us! Hey!
Hello!
Hello! On the test.
Trying to get stuff ready. Yes, what was the question again?
The question is, why do we bother doing all those readings if they're not on the test?
Oh, okay. No, that was a very interesting question. I've been talking to that every day to my students, and a good question I would ask is, why do you say we went all the way, we did a traffic test, and let's say we're going to do a driver's license, and a lot of teaching was done. They were like more than 500 questions, possible questions, and all of them would never ever be tested. Now, I've never seen somebody running into the road when it's red robot, but it has never been tested. Yes, oh, I've never seen somebody take his hand and put it on a gas plate that is burning. Okay? But it's never tested in school. So they are life skill knowledge. When you learn these lessons, you have to carry them in life, basic. I've never seen someone trying to go to a shop to buy food and rather went into a shop to buy shoes rather, because you learn how to read, and those are basic skills that you learn and apply them in life. There is no reason that a student would want to see everything in life or everything that has been taught in class to be tested. For example, we know billions of words. You've seen billions of words, and half of them has never been tested in class. So I've never seen someone trying to go to Joburg and is taking the off-ramp to go to Mpumalanga because he cannot read. So,
okay, thank you, Fabian.
We learn, and we must carry them in life. You learn them to do other things in life. Thank you.
Thank you, Fabian. Okay, Senelisi says, I wish to get more clarity on why Earth is more habitable. Watch the course! It's the course! Arashuka says, is it true there are many other galaxies? Yes. Antisiwe says, why is the Earth habitable? Malati says, can we have lectures that include how plants affect the climate? Yes, definitely. When we introduce life, that will be there. And Nadewezo says, how many points do you have to score in order to qualify for the workshop? Well, that all depends on how many points other people score, because it's the top 30. So it's a relative question. I can't tell you that. Okay, that is all the short answer questions. What I want to say is to thank you all for your 2 hours. It's been really interesting. Thank you for your questions. We love getting them. Thank you to all the scientists here and in the other countries. You guys have been brilliant. We couldn't do it without you. And just that we couldn't possibly answer all of your questions. We did the best we could to pick some of the interesting ones. But that lots of you asked questions which involved a lot to do with life or humans. We haven't put life or humans into the model. So anything with climate change or people or most of the things with trees and plants and animals, I moved those questions into the next 2 sessions. So we'll hopefully get to them then. It's been great doing the course with you guys. Thank you very much, and we'll see you again for the next session. Cheers.